In continuing our sort of general fascination with prime numbers in this channel, we're going to introduce a rather intriguing set of primes known as Wilson primes. Now, these are primes that are named after the English mathematician John Wilson, and they're rather intriguing because so far we only know of 3 Wilson primes. Now, a prime number p is a Wilson prime if p minus 1 factorial plus 1 can be perfectly divided by p squared. So if p squared divides p minus 1 factorial plus 1, then p is a Wilson prime. Now, the only 3 Wilson primes that are known to us are 5, 13 and 563. So let's see whether you can actually work out that 5 and 13 are Wilson primes. So let's look at a little bit more in detail about these rather curious primes known as Wilson primes. The reason we say they're curious is because so far we only know 3 of them. Let's just remind ourselves what the definition of Wilson primes are. So let's imagine that you have a prime number p such that p minus 1 factorial plus 1 is perfectly divisible by p squared. So if you have a prime number p such that this is satisfied, i.e. p minus 1 factorial plus 1 is perfectly divisible by p squared, then the prime number p is a Wilson prime. Let's just remind ourselves what a factorial function is. So just to remind ourselves what a factorial function is, let's do that through an example. So 4 factorial would be just 4 times 3 times 2 times 1. So that's a factorial function, and that's the factorial of 4. So let's look at the first prime number. So the first prime number is 2. So what we do is we stick it into this expression here, and we get 2 minus 1 factorial plus 1 and divide that by 2 squared. So we'll get 2 minus 1 is 1, 1 factorial is 1, 1 plus 1 is 2, divide that by 2 squares is 4. So that's not perfectly divisible, so 2 is not a Wilson prime. Let's look at the next prime number, which is 3. So in a similar manner, we get 3 minus 1 factorial plus 1 divided by 3 squared. So 3 minus 1 is 2, 2 factorial is 2, 2 plus 1 is 3, divide that by 3 squared, so 9. It's not perfectly divisible, so 3 is also not a Wilson prime. Now moving on to 5, we get, which is the next prime number, we get 5 minus 1 factorial plus 1 divided by 5 squared. So that 5 minus 1 is 4, so that is 4 factorial plus 1 divided by 5 square, which is 25. So 4 factorial is just 4 times 3 times 2 times 1, and we need to add 1 as well, divide that by 25. So that's 4 times 3, 12, times 2, 24, times 1, 24, plus 1 is 25. So we get 25 divided by 25. So that's perfectly divisible. So 5 indeed is a Wilson prime, and it is the very first Wilson prime. Now, we had already said that the next Wilson prime is 13. To check that, we would do 13 minus 1 factorial plus 1 divided by 13 squared. So 13 minus 1 is 12 factorial plus 1. So we get 12 factorial plus 1 divided by 13 squared, which is 169. Now we will need some help with the calculator to work out 12 factorial. It's a sort of rather large number. And when we do that, we get 479,001,600. So that is 12 factorial. You add 1 to it and divide it by 169. When we do that, we get another largish number, but that number turns out to be 283, 4329, and that is perfectly divisible. So 13 is indeed a Wilson prime. Now, we had said that we know 3 Wilson primes, and the third Wilson prime is 563. So this is the third known Wilson prime, and we're going to leave you with a question, and you can almost anticipate what the question is going to be. And the question is, can you show that 563 is a Wilson prime? So that's the question for you. Can you actually show that 563 is indeed a Wilson prime?